All right, so now let's talk about a technical application of solution chemistry, which is osmotic pressure. Osmotic pressure is a useful measurement that we can do to help calculate the molar mass of a large molecule. For example, this is a very simple way that you can figure out what the molar mass, that is to say, what the molecular weight is of proteins, for instance, which are large biological macromolecules. So to define osmotic pressure, which we denote with a big capital Greek letter pi, okay, hence this pi here, I would like you to consider a solvent and a solution. So the solution is whatever your solvent is with your solute dissolved in it. The solute could be, for example, a protein. Let's imagine that we have the solvent, the pure solvent, and the solution of the solute plus the solvent separated from each other in a U-shaped tube. Okay, so here's my U-shaped tube. In this U-shaped tube, they are separated by a semi-permeable membrane. Semi-permeable in this case means that solvent molecules can pass through, but solute particles cannot. Now, this makes sense if we have a large macromolecule. The large macromolecule cannot pass through the semi-permeable membrane, but the small solvent molecules can pass through the semi-permeable membrane. Okay, so imagine we have a U-shaped tube. We have this membrane here, this semi-permeable membrane, and solvent molecules can pass through the membrane, but solute cannot. So through osmosis, you are going to have solvent particles travel across the membrane to the solution side, and they are going to essentially dilute that solution. So through osmosis, solvent molecules will migrate to the solution side through that semi-impermeable membrane. And they will keep on moving through the membrane until the liquid levels stop changing. Okay, we call that equilibrium. So until some kind of equilibrium is reached and the liquid levels stop changing. So if you go back to the first one, you can see where I kind of noted where the top of the liquid is here and here. What's going to happen is the solution is going to be much taller and the solvent side will have gotten much shorter. Okay, so this is the solvent side, and many of the solvent particles migrated over to the solution side. Now, at equilibrium, the height difference between these two, okay, so this is the height difference here, represents what's called the osmotic pressure pi. Okay, so the height difference at equilibrium is the osmotic pressure, pi. This is the pressure that you would have to put on it to make the heights of each side equal again, to bring those two sides back to equal height. Now, we can write an equation for pi, just like the ideal gas law. This is literally a pressure. You can measure it in millimeters, just like we measure pressure in millimeters of mercury. So osmotic pressure pi can be calculated with something like the ideal gas law. Remember PV equals nRT? If PV equals nRT, then P equals nRT over V. So we can write something similar for osmotic pressure. Pi, the pressure, equals N over V times RT. This is just a version of the ideal gas law, Pivner, even though we're talking about liquids here. Now, the reason I wrote it this way is because I wanted moles per volume. Moles of solute per volume of solution. You should recognize that. That's molarity. Okay, that's going to be the molarity of your solution. The R that you want to use here is the same R that you use in the ideal gas law. That's going to be 0.08206 liter atmospheres per mole Kelvin. So your osmotic pressure is often measured in torr, right, which is millimeters of mercury. You have to convert that to liters, to atmospheres rather, to use this equation. Finally, because of the gas constant, you need to put your temperature always, always, always in the Kelvin scale. Okay, so this is just a rearrangement of the ideal gas law, PV equals nRT. Let's put this equation into practice. Here is an example. I have a protein sample. Okay, remember, protein is a large biological molecule. It's a macromolecule. So I have a 0.15 gram protein sample dissolved in water to give a 2 milliliter solution. The osmotic pressure of that solution is 18.6 torr at 25 degrees Celsius. Now remember, torr is equivalent to millimeters of mercury, so it's like measuring a height, millimeters, right? So the osmotic pressure of this protein solution is 18.6 torr at 25 degrees Celsius. Using that information and the formula for osmotic pressure, can we calculate the molar mass of the protein? All right, so I want to emphasize here, molar mass is molecular weight, and the units are going to be grams per mole. So we need to figure out how many moles there are so we can put it in the denominator. We'll put 0.15 grams over however many moles that corresponds to, and that's going to give us the molecular weight. So the first step is that you must take that osmotic pressure and change it to atmospheres so that you can plug it into the equation. Now we know that there are 760 torr in 1 atmosphere. So that unit conversion tells us that I have an osmotic pressure of 0.0245 atmospheres. Now, I can take that and plug it into the equation. Pi equals N over V times RT. That means that N is going to be equal to pi times V over RT. Again, this is just kind of like a rearrangement of the ideal gas law. So I'm going to have, 0.0245 atmospheres multiplied by the volume. Okay, so I was told the total volume is 2 milliliters, and I need to make sure that I convert that to liters because I need to cancel out with the units of the gas constant. So that's 2 milliliters is 0.002 liters, and that's going to be over R, 0.08206 liter atmospheres per mole Kelvin, times T, and T is 25 degrees Celsius, so that's 298 Kelvin. So keep track of your units here. They are your friends. You can cancel out the atmospheres and the kelvins and the liters, and moles is in the denominator of the denominator. So the moles flip to the top, and this gives me the number of moles of protein as 2.0 times 10 to the minus 6 moles of protein. And I know from the problem that I have 0.15 grams of protein. So the molar mass of the protein, or molecular weight, molar mass is a synonym for molecular weight, is going to be equal to 0.15 grams over moles. Again, molar mass is going to be grams per mole. I have this many moles of protein corresponding to that many grams of protein. That's what the calculation tells me. So this should be a huge number because proteins are really big. So they're going to have really big molecular weights. I'm going to round it. It's about 75,000 grams per mole. A molecular weight like that makes a whole lot of sense for a protein, which is a large biomolecule. So you can use osmotic pressure to calculate the molecular weight of a mystery solute, particularly a large one, something that's not going to pass through that semi-permeable membrane.